Nuclear War Survival Skills, Part 2, Chapter Number 1. The Dangers from Nuclear Weapons, Myths and Facts. An all-out nuclear war between Russia and the United States would be the worst catastrophe in history. A tragedy so huge, it is difficult to comprehend. Even so, it would be far from the end of human life on Earth. The dangers from nuclear weapons have been distorted and exaggerated for varied reasons. These exaggerations have become demoralizing myths believed by millions of Americans. While working with hundreds of Americans building expedient shelters and life support equipment, I have found that many people at first see no sense in talking about details of survival skills. Those who hold exaggerated beliefs
Grief is the normal human response to the loss of a loved one. You hear a lot of people say,
where the fuck was that? While working with hundreds of Americans building expedient shelters and life support equipment, I have found that many people at first see no sense in talking about details of survival skills. Those who exaggerated beliefs about the dangers from nuclear weapons must first be convinced that nuclear war would not inevitably be the end of them and everything worthwhile. Only after they have begun to question the truth of these myths do they become interested. Under normal peacetime conditions, in acquiring nuclear war survival skills, therefore, before giving detailed instructions for making and using survival equipment, we will examine the most harmful of the myths about nuclear war dangers, along with some of the grim facts. Myth: fallout radiation from a nuclear war would poison the air and all parts of the environment. It would kill everyone. This is the demoralizing message of On the Beach and many similar pseudo-scientific books and articles. Facts: when a nuclear weapon explodes near enough to the ground for its fireball to touch the ground, it forms a crater. See figure 1.1. Many thousands of tons of earth from the crater of a large explosion are pulverized into trillions of particles. Figure 1.1. A surface burst. In a surface or near surface burst, the fireball touches the ground and blasts a crater. It shows the blast making a crater in the earth. It shows light and heat going up. It shows radiation going up and curving. It shows initial nuclear shooting out the side. And it shows radiation kind of shooting out at a 45-degree angle and then going down. In this picture, it shows the blast hitting the earth. It shows the fallout particles starting to fall. So it hits the earth, and then it shoots up into a cloud. And then it shows the fallout particles starting to fall. Figure 1.1, a surface burst. In a surface or near surface burst, the fireball touches the ground and blasts a crater. Okay. And then it shows the wind going this way, and you can see the cloud going more that way. These particles are contaminated by radioactive atoms produced by the nuclear explosion. Thousands of tons of the particles are carried up into the mushroom-shaped cloud, miles above the Earth. These radioactive particles then fall out of the mushroom cloud, or out of the dispersing cloud of particles blown by the winds, thus becoming a fallout. Each contaminated particle continuously gives off invisible radiation, much like a tiny X-ray machine. While in the mushroom cloud, while descending and having fallen to Earth, the descending radioactive particles are carried by the winds, like the sand and dust particles of a miles-thick sandstorm cloud, except that they usually are blown at lower speeds, and in many areas, the particles are so far apart that no cloud is seen. The largest, heaviest fallout particles reach the ground first, in locations close to the explosion. Many smaller particles are carried by the winds for tens to thousands of miles before falling to Earth. At any one place where fallout from a single explosion is being deposited on the ground in concentrations high enough to require the use of shelters, deposition will be completed within a few hours. The smallest fallout particles, those tiny enough to be inhaled into a person's lungs, are invisible to the naked eye. These tiny particles would fall so slowly from the 4-mile or greater heights to which they would be injected by currently deployed Soviet warheads, that most would remain airborne for weeks to years before reaching the ground. By that time, their extremely wide dispersal and radioactive decay would make them much less dangerous. Only where such tiny particles are promptly brought to Earth by rain-outs or snow-outs in scattered high spots, and later dried and blown about by the winds, would these invisible particles constitute a long-term and relatively minor post-attack danger. The air in properly designed fallout shelters, even those without air filters, is free of radioactive particles and safe to breathe, except in a few rare environments, as will be explained later. Fortunately, for all living things, the danger from fallout radiation lessens with time. The radioactive decay, as this lessening is called, is rapid at first, then gets slower and slower. The dose rate, the amount of radiation received per hour, decreases accordingly. Figure 1.2 illustrates the rapidity of the decay of radiation from fallout during the first 2 days after the nuclear explosion that produced it. R stands for Roentgen, a measurement unit often used to measure exposure to gamma rays and X-rays. Fallout meters, called dosimeters, measure the dose received by recording the number of R. Fallout meters, called survey meters or dose rate meters, measure the dose rate by recording the number of R being received per hour at the time of measurement. Notice that it takes about 7 times as long for the dose rate to decay. Figure 1.2. The decay of the dose rate of radiation from fallout from the time of the explosion, not from the time of fallout deposition. It shows on this side from 0 to 1,000 is the dose rate. The dose rate R/HR, which I'm thinking is like an hour or whatever. Maybe the rate per hour. Okay. And then on the bottom to the right is the numbers 0 through 7, 14. This is the hours after the explosion. Okay. So the bottom part of the scale is the hours after the explosion. At the end of that is 10 R/HR, and it says 48 hours after. So you have from 0 to 48 hours on the bottom part of the scale. And on the left side, you have the dose rate from 0 to 1,000. It shows at the beginning, you have 1,000 dose rate on the top, and that's 1 hour after the initial explosion. By 2 hours, you're at 480 Rs an hour. At 7 hours after, you're at 100 radiations things an hour. At 14 hours, you're at only 43 Rs an hour. And ultimately, here at the end, you're only at 10 Rs an hour, and that's 2 days after the initial explosion.